Okay, so welcome back, everybody. This is the 8th week of class, if I'm not mistaken. And just to give you kind of a roadmap as to where we're going in the next few weeks, next week we'll finish up this lecture on Newton's laws, and we'll start the next chapter, which is on the applications of Newton's laws. But then the week after that, we'll be on spring break for an entire week. And when we come back from spring break, we'll resume talking about the applications of Newton's laws. I'm also going to let you know that I'm giving you a quiz the next time we meet for lecture, which is next week on Tuesday. As usual with quizzes, I'm going to give it out right at the beginning of class, so try to make it here on time and don't be late so you have plenty of time to work on it. It's going to be a short quiz, about 15 minutes in length, like the other ones you've seen, and the topic is going to be Newton's laws. Okay, so do we have any questions about that? Nope. All right, so let's get back into the lecture in that case. This is where we left off. We were doing a bunch of example problems involving the third law of motion. This is the idea where we have equal and opposite forces. And this is just another example like that. So let's take a look at what's going on here. We have a chain of 3 monkeys hanging vertically from a tree branch, as you see here. Now, in this case, we're going to suppose that the entire chain of monkeys is at rest. So there's no motion happening. Each monkey has a mass of 12 kilograms. So my question for you is, what is the magnitude of the force that monkey number 1 has to exert on monkey number 2 in order to hold up this entire chain? Okay, that's the question. So take a couple minutes to try to work this out. And what I would suggest is drawing a 3-body diagram of all the monkeys in this picture. And the unknown force that you're trying to solve for is F12, the force that monkey number 1 exerts on monkey number 2. So take a minute and then we'll go through it together. That's right. Let's see if you can draw the diagram showing all the different forces there. All right. Do we have any initial thoughts on this? I saw that a few people just got it right away because there's sort of a shortcut to this problem. Anyone have the answer? You want to shout it out? I know some of you have it. So here, the short way of thinking about this is monkey number 1 needs to pull up with enough force to support the weight of monkeys 2 and 3. Right? So the force that needs to be supplied here is basically the combined weight of the 2 monkeys below it. Right? That's kind of the intuitive way of looking at this. So let's start there. So again, the idea is monkey number 1 needs to support the weight of numbers 2 and 3 below it. Okay, so that would be just m times g plus m times g if we think about the amount of force that would require, because we're supporting the weight of two monkeys, each one m times g. And they're not different masses, so we don't need to label them as m1, m2, just call it m, because they're all the same mass. So that's just 2 times mg, and that's 2 times, okay, we have 12 kilograms for the mass, and we have 9.8 meters per second squared per g. So what does that work out to? Yep, so we need 235 newtons of force to do this, okay? All right, so we're going to do this the long way now, okay? And the long way, it might seem to you like unnecessarily complicated at first, but here's the thing. When you get to more complex problems, you really need a systematic way to work them out. So following these steps is actually important, just to know in general. So what I'm going to do here is show you a free body diagram of each monkey. Okay? So remember, we have monkey 3 on the bottom, and then 2 in the middle, and then 1 at the top of this chain. So let's start with number 3, the one that's at the bottom. What forces are acting there? So yeah, the weight of this monkey, which I could call WE3 because it's exerted by the earth and it's acting on monkey number 3. But then there's some kind of upward force that's acting on the monkey because the monkey's not moving, right? The forces need to be balanced out. If it was just the weight, the monkey would be in free fall. But there's this upward force balancing out the weight that makes sure the monkey is not moving. So here's what I'm going to call that force. F23. See, monkey number 2 is up here, and monkey number 2 is pulling up with some amount of force, which I'm calling F23, to keep monkey number 3 in place. Okay. All right, let's do number 2. So what forces are acting on monkey number 2?
Its weight.
Its own weight. Okay, what else?
Normal force of monkey number 1.
Yeah, so monkey number 1 is up here, pulling up with some amount of force, right? I'm going to call that F12, because it's the force that monkey number 1 is exerting on monkey number 2. Is there anything else going on here?
Monkey 3.
Yeah, so here's the thing. This force we labeled over here does not just exist in isolation. If 2 is exerting a force on 3, 3 is exerting a force back on 2, and that force has to appear in the free body diagram for monkey number 2, because here we're showing all the forces acting on monkey number 2. What direction should I show that force? It's down, right? Because if this one is up, the equal but opposite force is pointing down. So this is F32. And what I'll show is a little hash mark to denote that these are equal and opposite forces. All right, let's do number 1. Okay, so what are my forces here?
You'll have the weight of the earth going down, and then you'll have both of them on the as well.
Yeah, so I'm going to call this WE1, because again, it's exerted by the earth on monkey number 1. It's just the force of gravity, aka the weight. What else do I have going down?
Monkey number 1 and monkey.
So here I have F21. This is the force that number 2 is exerting on number 1. So again, if 1 is exerting a force on 2, that's going up, then 2 is exerting a force on 1, that's going down. And these are equal yet opposite forces, so I'll show that with a little slash mark, okay? So again, you got to get used to making these sorts of diagrams with this kind of notation, okay? And then what else is there in this picture? There must be some kind of upward force. What would be providing that upward force? So monkey number one is at the very top, the one that's hanging to the tree branch, right? So that tree branch, I'll call that B, is exerting a force on monkey number one like this, okay? So that's the complete accounting of the forces that are acting on all the different monkeys here, okay? So what we're gonna do next is apply the second law to each monkey. And we can just focus on the y direction because all of these forces are completely vertical. There's no horizontal forces, okay? So we're going to do Fy equals MAY on each one of these, okay? And we're going to start with number 3. All right, so with number 3, how do I add these two forces together? Well, I have one force going up and another force going down, okay? So let's be clear about what this equation says. It says add the forces in the y direction. So if I have a force going up, F23, I can write the y component as just positive the magnitude F23. If I have this force WE3 going down, I can write that as minus the magnitude WE3, just to pick out its y component, okay? And then I have m times whatever acceleration the monkeys may have. We actually know in this case it's 0 because nothing's moving, but just for now, I'm going to leave that ay as a variable. We'll plug in 0 for that later. Does that make sense? We're not accelerating, but I'm going to leave it for now, okay? Okay, cool. So if I solve for F23, that would just be equal to MAY plus the weight, right? Because I can just throw this over on this side of the equation. And the weight is given by m times g. We good on that? Okay, so let's now do the same thing for monkey number 2. We look at all the forces acting on it. We add up the y components. That's supposed to be equal to m times ay. All right, so looking at this diagram, what forces are in the positive direction? F12. So I'll take the magnitude F12, and then I'll subtract the magnitude of these two forces. That's how I add these y components together. So minus F32 minus WE2. That equals MAY. And again, I'm just using the same m value for all these different objects because they all have the same mass. Okay? If they had different masses, I would want to label them like M1, M2, and so on, but they have the same mass, so I don't need to do that. So I have F12. By the way, this is the force we want to know. That's the force that monkey number 1 is exerting on monkey number 2. Remember, that's the whole point of this problem. This is how we did it the short way. If I solve for that, I'm going to get MAY, and I have to take these two forces, remember, and then add them to this side of the equation to solve for F12, okay? So first we have magnitude F32. Well, we found that up here, right? This is this result, so I'm going to plug that right in. That's MAY plus MG. And then I'm adding WE2 to this side, which is just MG. So look, I have two terms that are MG, two terms that are MAY. So I can kind of consolidate that to say 2M times AY plus G. So that's the force that one has to exert on 2. But now we'll use the fact that there's no motion. So AY is just equal to 0. Okay, so that means the force we're looking for is just 2 times m times g, because AY is going to 0. All right? So what we do is we plug in 2 times the mass of each monkey, which is 12 kilograms, multiplied by g, which is 9.8 meters per second squared. and we get the same answer I showed you before, 235 newtons. Okay? So again, this is something you can probably just know intuitively, just by the fact that the monkey at the top of the chain has to support the weight of all the ones below it. And if there's 2 below it, then we have 2 weights, 2 times mg to support. And that should be fairly intuitive, right? But if we analyze it in all its gory detail, this is what it looks like. And again, for problems that don't have an intuitive solution that you can just see right away, you have to know this kind of process, all right? Because it's the only way to go. Do we have any questions? All right, so let's keep moving. A follow-up to that, and by the way, this is why I kind of worked this out the long way. It's because now we have that result from before. You can answer this question really simply. So now we have the same chain of monkeys, all with a mass of 12 kilograms, just like before. But now what's happening is they're not just stationary. Now monkey number 1 is going to be pulling up on these 2, such that they accelerate up with an acceleration of 2.5 meters per second squared. No, I'm sorry. We're accelerating down at 2.5 meters per second squared. Okay? So if we're accelerating down at 2.5 meters per second squared, the question is, what is the force that monkey number 1 exerts on monkey number 2 for this motion? Let me just ask you this. You can do the calculation in a second, but is this going to be more or less force than what we found before? So if we're comparing the force just to hold everything still versus the force to lower, accelerate down, is this going to be less than before or more than before?
Right.
Yeah, you might imagine this takes less force, right? And that's what you should be seeing. So use what we found before. The formula is 2m_ay plus g. And just use it in this situation. See what you get, okay? All right, so what are we getting?
175.2.
Yeah, I think I agree with that. 175 newtons of force, so less than before. Okay, let's work this one out. So again, we've set up most of the work we need to answer the question. So we have F(1), the magnitude of that force, is equal to 2m times ay plus g. So we'll take 2 times the mass, which is 12 kilograms. Okay, what should I put in for ay? It's the acceleration, right? In the y direction?
Negative 2.5.
Yeah, because we're accelerating downwards. That would be negative 2.5 meters per second squared. By the way, if we were accelerating upwards, you would put a positive sign there, and you would get a larger force. But here, there's a negative sign which reduces the force, okay? And then we have plus 9.8 meters per second squared. So that's ay plus g. And yeah, that works out to 175 newtons. So it takes less force to accelerate everything down than just to hold everything stationary. And of course, it would take even more force to accelerate everything up, right? So that's the idea. Any questions? All right. So the next thing we'll do is inclined planes. Basically, this is a very common situation where something may be sliding down a ramp or down a hill, maybe moving up a ramp. We're going to see how to use Newton's laws to deal with this kind of situation. Okay? So here's the general situation. We're going to be thinking about some kind of mass on an inclined plane. So just think of like a block on a ramp. Okay? And for now, we're going to ignore friction. We don't yet have the equations we need to deal with friction that may be acting on something that's sliding down a ramp. We'll get to that in the next chapter. But my question here pertains to the normal force. Okay? So if we have this block resting on the ramp, we have this notion that there's a normal force that the ramp pushes on the block with. What is the direction of that force? Obviously, you don't have to give me an angle in degrees, but generally speaking, which quadrant is the normal force going into?
Or one.
The first quadrant?
Yeah. And is it going straight up or is it at an angle? Yeah. So here's the thing to remember. Normal forces, the word normal means perpendicular to your surface, right? And in a situation where your surface is flat, like this table in front of me, the normal force it would exert would be straight up, right? Because that's the direction perpendicular to the surface of the table. But as soon as we angle that surface, that changes the direction of the normal force. Now it's pointing in this direction, okay? Okay, what about the force of gravity? What direction would that be in?
It's down.
It's straight down, yeah. So the normal force changes direction as you angle the ramp, but gravity doesn't care about the fact that you're on a ramp. It's always just straight down, right? So if we have an inclined plane, my point is this is your free body diagram. Again, we're assuming no friction here. If there were friction, that would be an additional force on this diagram, but for now, we're ignoring that. So all we have really is the weight of the block and the normal force. Those are just the only two forces we're dealing with. So I'm going to show you sort of a trick that's commonly used when we deal with ramps and inclined planes. So up until this point, when we deal with our coordinate directions, we've been assuming x is horizontal and y is vertical, right? But what I want to show you here is that it's convenient to rotate your coordinates so that x is pointing parallel to the ramp, so let's say it's going down the ramp, and then y is perpendicular to the surface of the ramp like this. Okay, that's a convenient way to rotate the coordinate system. And that's what we'll do for what follows. All right, so like I mentioned, the only forces are weight and normal force. So when we show the free body diagram of the block, this is what it looks like. You have your weight going straight down. Okay, the direction of your W vector is not affected by the fact that we're on a ramp. It's always just straight down because that's the force of gravity. But your normal force is, again, going perpendicular to the surface of the ramp, so it's off at some angle like this. Okay? But remember, we're working in this coordinate system, which has been rotated such that the x-axis is going down the ramp, the y-axis is coming out of the ramp like this. So if we want to break our vectors, the n vector and the w vector, into components, here's how it's going to work, okay? So for the normal force, can you just see by looking at this diagram that it only has a y component, it has no x component? There's no part of the normal force that's going up or down the ramp. So nx is 0. And because the x component is 0, that means it's only in the y direction. So ny is just equal to the magnitude of the normal force. Does that make sense? Whenever you have a vector that has 0 components except for 1, that last remaining non-zero component is just equal to your magnitude. Okay, so we have ny equals the magnitude of that. Okay, for the weight, again, if we had the y direction just going vertically, then the weight would be just in the negative y direction. But remember, we've rotated our coordinates. So now the weight vector has both x and y components. You can actually see what they are here. This is wx, that's the component of my weight that's going down the ramp. And this is wy, that's the component of the weight that's going perpendicular to the ramp. Okay? And if we want to break this up, we need some kind of angle. So usually when it comes to a ramp, to indicate how steep it is, we give the angle of the ramp surface relative to the horizontal. So we're going to call that angle from this point on theta. Okay, so if theta is really close to 0, you have a very shallow incline, and if theta is very big, close to 90, you have a really steep incline. So the angle theta that you see here appears right here in our vector diagram. It's the angle between wy and magnitude w right here. Is that straightforward to see, or do you want to go over that? How this angle in the diagram is the same as this angle for the ramp? What do you think? No comment? Okay, let's go through it. So what I'm trying to show you here is that, so this is the angle theta for our ramp, right? And this dashed line is the y direction, basically. Okay? And our w vector is pointing straight down like this, okay? All right, so let's just do a little geometry. See this angle I'm pointing to right here? How could we work out what that angle is? Well, we have a triangle, right? And what do the angles in a triangle have to add up to?
180.
180. So this would be 180 minus the two angles here and here. Well, this angle right here is 90 degrees. And then this angle right here is theta, right? So that's 180 minus 90 minus theta. What's 180 minus 90? That's just 90, right? So this angle I'm pointing to is 90 minus theta. So this angle I'm going to point to over here, what does that have to be equal to? The double slashes, what is that one equal to?
90.
It's not equal to 90.
180?
What you should be seeing is the single slashed angle and the double slashed angle. Those add to 90, right? So this is just going to be equal to theta, okay? So that's our angle theta. So that's what I was trying to show you, is that this angle right here is the same as the angle of our ramp itself, okay? These are the same thing. All right? Any questions? All right, so how do we work out the geometry then? Well, theta is our angle here in this diagram, and the magnitude of this vector w is our hypotenuse, right? So this side over here, what would we call that? Opposite, adjacent, hypotenuse? This would be our adjacent side right here, wy, okay? And what trig function does adjacent go with? It goes with cosine, right? Let's think about it. Cosine of this angle theta is adjacent divided by hypotenuse. It's wy divided by the magnitude of w, right? And the magnitude of w is just mg. Remember, that's the strength of this force. So wy is just mg cosine theta. But there's a negative sign because it's going in the negative direction, okay? All right, how does sine work? Sine is opposite over hypotenuse. That would be this opposite side, wx, divided by this hypotenuse, which is the magnitude of our weight vector. So therefore, wx is mg sine theta, okay? And it's going in the positive direction, so we don't need to tack on a negative sign there. So that's how this vector breaks up into components, okay? So with that said, we can apply Newton's second law to each coordinate direction, right? We have the net force in the x direction equals max, and then we have the net force in the y direction equals may. So here, let me ask you this. Remember, x is the direction just going down the ramp. Y is the direction going perpendicular to it. So if you have a block sliding down a ramp, which one of these accelerations is going to be 0? Either ax or ay. Yeah, your acceleration in the y direction is 0 because you're only moving in the x direction. You're only moving down the ramp. You're not moving perpendicular to the surface of it. So we could say ay is equal to 0. But ax, that's not necessarily 0, right? All right, so ay is equal to 0 because for the whole time the block is just in contact with the surface of the ramp. It's not moving perpendicular to the surface of the ramp. And so if we look at equation number 2, that's the one that involves ay. Remember how this works. We take the sum of all the forces in the y direction. So that's the normal force in the y direction, and that's the weight in the y direction. We're taking those two y components and adding them together. But my acceleration in the y direction is 0. So this right-hand side of the equation becomes 0. And if we remember how these forces broke down into components, remember the normal force in the y direction is just the full-on magnitude of it. And the weight in the y direction was minus mg cosine theta. So we have the normal force minus mg cosine theta equaling 0. And that means the normal force is equal to mg cosine theta. Okay, so this is a general result when you're on a ramp. The normal force is given by mg cosine theta. If you're on a flat surface, it's just given by mg. If you're just resting on a flat surface, but when you tilt that surface, we pick up this cosine theta factor. Okay. All right. If we look at equation number 1, let's take a look at how this works. So equation number 1 says we have the net force in the x direction. So we're going to add up the x components, nx and wx, and that's going to give us m times ax, right? Now remember, the acceleration in the x direction is not 0, so I'm just going to call that a, and we'll not necessarily try to guess what its value is. We'll leave it as an unknown. Okay, normal force. What's the x component of that?
0.
It's 0, right? There's only a normal force in the y direction, not in the x direction, using this tilted coordinate system. And what do we have for wx? What was that again? Just worked it out. So this was mg sine theta. Okay, so here's what we have. We have 0 plus mg sine theta equals ma. And what can I do to simplify this?
Divide up mass.
Divide out the mass, cancels out here, and it cancels out here. So we get A equals G sine theta. Okay? So we have two results here. We have the normal force acting on the object as it slides down the ramp, and we have the acceleration down the ramp. A is just equal to G sine theta. And again, this all assumes no friction. If there is friction, this gets a little more complicated, but we'll learn how to deal with that in the next chapter. So, any questions on how we got these results? All right. So here, whenever pretty much any physics problem you do, you want to take a look at the results you're getting and see if they make sense. Try to kind of test them out real quick. So, what I'm going to do is take the two results that we got for the normal force and for the acceleration, And just look at what happens in the two extremes, where theta is equal to 0, which means the surface is perfectly flat and there's no incline at all. And then theta equals 90 degrees, where it's a vertical drop. And we'll see what happens in each case, and just make sure that it makes sense, okay? So remember, we're dealing with an object sliding down an inclined plane with no friction. So if we look at the normal force, in general, right, if n is equal to mg cos theta, the normal force is less than the weight. It's less than mg. Okay, because cos theta is generally going to be something less than 1. But here, let me ask you this. Cosine theta, if we take theta to equal 0, what comes out? So, in other words, what is the cosine of 0?
1.
Cosine of 0 gives you 1, right? So then you just have mg times 1. So you just have mg. Does that make sense? When we set the angle to 0, you're just resting on a flat surface. So the normal force up from that surface is just exactly equal to the weight in that case. All right, but let's take the other extreme. Theta goes to 90 degrees. In that case, what is the cosine of 90 degrees? Cosine of 90.
0.
That's 0. So your normal force goes to 0. Does that make sense? So 90 degrees means we have a completely vertical incline like this. And in that situation, you would just lose contact with the incline. So yeah, you'd have no 0 normal force, right? That makes sense too. Let's take a look at the acceleration. And again, plug in 0, plug in 90 degrees, and see what comes out. So, all right, for the acceleration, we have g sine theta. If I plug in theta equals 0 degrees, what is the sine of 0 degrees?
0.
That's just 0. So you get 0 acceleration. That says, if you're on a flat surface with no incline, you don't accelerate up or down the incline, right? That makes sense. No acceleration. In the other extreme, we have 90 degrees. What's sine of 90 degrees?
1.
That's 1. And in which case, your acceleration goes to g. That means you're in free fall, right? You have a perfectly vertical drop, so you're just in free fall, and the acceleration is equal to g. That's what we would expect, okay? So this is what I mean by check your answer. You can look at the expressions we got and see that they make sense. If we tried this stuff out and the results didn't make sense, it would indicate we made a mistake earlier and we want to go back to check the work. Right? That's the idea. Okay, so here's a question for you. An object is sliding down a frictionless ramp with an acceleration that is half of g. So a is half of g. What is the angle of the ramp in degrees? Of course, yeah, no friction is the assumption here. So use the result we just got, that a is equal to g sine theta, to solve for theta, the angle of the ramp. All right, so what are we getting for this?
30 degrees.
30 degrees, yeah? We agree? All right, so this is what we're doing. We're saying A is equal to g sine theta. That's your acceleration down the ramp. And what we're saying is that A is half of the free fall acceleration. So we're going to use 1/2 g equals g sine theta. So g cancels, and we just have sine theta equals 1/2. So this might be one of those from the unit circle that you remember, right? If the angle is 30 degrees, the sine of that angle is 1/2. Or you can just go to your calculator and type in inverse sine of 1/2. Either way, you should see that the answer is going to be 30 degrees. Okay? All right, any questions on that? All right, so here's another question. Now, before we even get into the question, I just want to remind you of something very general. What we did is we used Newton's laws to solve for the acceleration of an object sliding down a ramp with no friction. So we got that general result for the acceleration using Newton's laws. But once you have that, you can use that result in your kinematic equations to say, predict how something will move. You know, how fast will it be moving? Where will it be located at a certain time? So you use Newton's laws and kinematics together to fully describe how motion is going. So this is an example of that. A box is held at the top of a frictionless ramp that's 12 meters long and is angled at 15 degrees with respect to the horizontal. So what we do is we release the box from rest, it slides down to the bottom of the ramp. How long does that take? How long does it take to slide from the top of the ramp all the way to the bottom? So try to work this out. Again, you're going to use the acceleration formula we just found, as well as kinematic equations to work this one out. Okay? So here, let me give you a hint on what the kinematic equation should be. Try this. Try doing x equals x naught plus v naught x times time plus 1/2 ax t squared. Hopefully that looks familiar, right? So try using this to solve for the time in this situation. For your acceleration, it's going to be g sine theta. All right? So these are your formulas. Try to work it out from there, okay? So go back to the slide so you know what the numbers are. Well, you can't use that because we're at an angle of 15 degrees. So it's not just going to be free fall acceleration, it's going to be g times the sine of 15 degrees. Okay, I see a few of you have this one already. Let's go through it. So, here, let's start with this. Let's draw a picture. This might make things easier to visualize. So we have the ramp, which is angled at theta equals 15 degrees. We start with the box up here at the top of the ramp. So now, what I'm going to do is draw a coordinate system that's tilted, where x is going down the ramp like this. That's our x direction. So, we have the starting position of the box over here, and then we have the final position of the box over here. The point is, there's a 12-meter distance between these two positions. So I could put 0 to be the initial position, and 12 meters to be the final. That would work because there's 12 meters between them. All right. What can we say about the initial velocity of the box? V0x. It's 0, right? Because we start at rest. So because we start at rest, the initial velocity that we're going to use in our kinematic equation is going to be 0. Okay, so the last thing to figure out here is what is our acceleration down the ramp? That's ax, our acceleration along the x-axis. Well, we worked that out. It's g sine theta. So it's 9.8 meters per second squared times the sine of 15 degrees. So I'm sure some of you worked this out. What is the acceleration?
2.53.
Yes, it's like 2.54 meters per second squared. Okay, so let's use all the information we have in the kinematic equation. So x, what does this variable represent in our kinematic equation? Just in words, what do we call that? That's the final position. That's what that represents. What is our final position here? So that's 12 meters equals, okay, what does x naught represent?
0.
Yeah, it is 0, but it's our initial position, right? Okay, v naught x, that's our initial velocity, also 0. And then we have a half times our acceleration, which is again something we find using Newton's laws, but here it is. 2.54 meters per second squared, and then we have t squared. So solving for that value of t is going to give us how long it takes to go all the way down the ramp. Okay? So here, t squared, if we solve for it, multiply by 2, and then divide by the acceleration, divide by 2.54. And now we have t squared equals that. If we square root on both sides, then we'll just have t. So what does this work out to?
3.1 seconds.
That's 3.1 seconds. So that's how long it takes to slide down the ramp from the very top to the bottom. Okay? All right, so I think for now, that's enough about ramps and inclined planes. Now let's move on to tension. So again, just to kind of orient you here, we know what Newton's laws are. We've worked with them a little bit. So what we're going to be doing for the next several weeks is just looking at different types of forces that exist in the real world and how to deal with them. So we've dealt with things like weight and normal forces. We're going to also deal with something called tension now, and I'll show you just some basic ideas about how to deal with this. So let's get into it. Okay, tension, in the most general sense, is a force that's transmitted along the length of an object, and it's a pulling force, okay? So if I were to take, I don't know, my jacket, let's say, or pull it from both ends, I'd be creating some tension within the jacket, okay? That tension would be acting along the length of the jacket. It's a pulling force that exists in this material. Same thing is true of a rope. When you pull both ends of a rope, you create some tension in that rope, okay? So normally, when we talk about tension, we're going to be referring to some kind of connecting rope or connecting string or connecting cable between two objects, but tension is more general than that, okay? Tension is just a force that exists in a material in general. So here, let's consider this situation that I'm showing you here. We have a box, it's connected to a rope, and at the other end of that rope is a person, okay? Now, I want you to imagine, just for a second, that this rope has no mass. M is equal to 0. Obviously, that's not very realistic, right? But we're going to derive the behavior of how this tension exists in the rope. And it's actually going to be valid for any situation where the mass of your string is negligible, okay? So it's not necessarily that it's exactly equal to 0, but it's a small mass compared to the box, okay? So, okay, let's draw a free body diagram of a few different things. Let's draw a free body diagram of the box. So this one is pretty straightforward. What we have is this force. There's a force going to the right that I'm going to call FSB. What does this mean? It's the force that the string here is exerting on the box. And again, I'm ignoring any vertical forces, so that's really it. Okay, next thing, let's draw a free body diagram of the string itself, okay? So let's consider this force. This is FBS. That's the force that the box is exerting on the string. Remember, these are equal and opposite forces. If the string is exerting a force on the box, then the box must be exerting a force back on the string in the opposite direction. So to show that these are equal and opposite forces, I put a little slash. Okay, but at the other end, we have the person's hand pulling on the other side of the string. So there's a force, which I'm going to call FHS. That's the force that the hand is exerting on the string, okay? So the string is being pulled in these two different directions from both sides. Does that make sense? Okay. So let's apply F equals MA to the string itself, okay? So we're going to add up the forces and set that equal to M times A for the string itself. Here's what you get. These two forces that I'm showing you here are added together, FBS plus FHS, okay? That's just what it means to take the sum of forces, as we add these two. But on this side, I'm setting that equal to 0. Here's why. Because what we're assuming is that the mass is equal to 0, okay? So if you plug in 0 on this side of the equation for mass, you get 0 for the entire right-hand side, okay? So that's all good. What does that tell us then? FBS is just the negative of FHS, right? It's being pulled with the same exact amount of force from either end, but in different directions. That's what the negative sign entails. So in terms of the magnitudes of these two forces, they're the same. In other words, there's the exact same amount of force pulling on this end as there is on that end. What that really means is that the force that this person is pulling with on this end is just transmitted all the way down the string to the box, and it doesn't get diminished at all. Whatever force you pull with over here is going to be felt at this end with the same exact amount of force. Okay? It's just transmitted undiminished along the length. Now, I just want to be clear. This idea that it's the exact same force transmitted along the string is only strictly true if we assume the mass is equal to 0. So in the real world, where you have cables with a mass that you can't ignore, like the cables on the Golden Gate Bridge or something, this gets a lot more complicated, okay? But if the mass is small enough that we can neglect it for a string or for a cable, then this is going to be true, okay? All right, so here's a situation we're commonly going to encounter, strings and pulleys working together. So remember, tension the force that's transmitted along the length of a string is going to be the same at either end. That's really important. So if we have a cable or a string connecting two objects, then it's the same amount of tension at either end of that string. And the other thing is, tension is transmitted along the length of the string. Okay? So if we have a pulley, basically what that allows us to do is change the direction of that tension force. For example, over here, the tension force that's acting on box number 1 is going to be horizontal because it's going along the length of the string. But acting on box number 2, it's going to be a vertical force because the pulleys change the direction that the string is oriented at. Okay? So what we see here is an example of this. If a string curves around a pulley, it will still have a constant tension along its length, assuming the mass is negligible. And if we connect two objects by a string, here's another thing we should see. They're going to move together, right? So if I allow box number 1 and box number 2 here to start moving, they're going to have basically the same acceleration. They can't accelerate at different rates because they're constrained to move together, okay? So that's a useful fact. Same tension at either end, and if we're connected by a string, same acceleration at either end, okay? So let's take a look at the free body diagrams of this situation here, where we have block 1 on the table and block 2 hanging vertically, okay? So block number 1. One force that definitely is acting on it is its own weight. So that's a downward facing arrow that I'm labeling as W1. Of course, since it's resting on a table, which is a flat surface, there's also a normal force acting on it, which is going up. Okay? So we have these two vertical forces which balance each other out. But since it's connected to the string here, there's going to be a force which I'm labeling as T for tension, acting on it and pulling it to the right. Because again, that tension force acts along the length of the string. And that's the free body diagram for block number 1, assuming there's no friction or anything else going on, okay? For block number 2, here's what it looks like. This is the one that's hanging vertically. So it's important to note that there isn't a normal force here. A normal force would occur if it's being supported by some surface, but that's not the case here. Instead, we have the weight of the block going down, that's W2, and then we have tension. But remember, tension acts along the length of the string, so in this case, the tension would be pulling the block upwards. All right? So that's just to illustrate, again, that what a pulley is doing is it's changing the direction of our tension force, but it's got the same magnitude at either end of that string. So, any questions on that? How this works? We're going to do an example of this. This is called an Atwood machine. It's a pretty simple machine. You have two masses which are hanging by a string, and that string curves around a pulley like this. So both of these masses are hanging vertically from a string which is connected to this pulley here. Okay? So remember, if we have two masses connected by a string, they have to move together. So they don't have two different accelerations that we have to solve for. They actually have the same acceleration. Okay? And what we're going to do is come up with a formula using Newton's second law for what that acceleration is. Okay? So here, let's think about this intuitively. Okay, let's say, just for the sake of argument, that M2 is a larger mass than M1. So which way is everything going to accelerate in that case? So M2 is bigger than M1. I hold the blocks like this, and then I let them go to start the motion. What direction would this guy accelerate in?
Up.
Yeah, so the less massive one would shoot up, and the more massive one would shoot down, right? So they accelerate in different directions, like this. But the magnitude of that acceleration is the same on both sides. That make sense? That's because they're connected. Okay. So let's go through it. So we're going to assume that block 1 is lighter, as I just said. So that means M1 is less than M2. Okay. So let's draw a free body diagram of each one of these blocks. And I'm going to use this coordinate system where the positive y direction is straight up. Let's do a free body diagram, FBD, for block 1. What are the forces that are acting on this block?
Tension.
We've got tension. Which way does it go?
Oh.
The tension pulls the block up. So I'm going to call that T. What else do we have?
Weight.
We have the weight. And notice I'm showing this as a smaller force than T because I know that it's accelerating up. So the net force is upwards. There's a bigger tension force going up than the weight going down, so it accelerates up. I'm just going to write that up over here. Accelerates upward. Okay? And I'm going to call this W1 because we're also going to have the weight of block 2, and I don't want to confuse it with that. Okay? Now let's do the free body diagram of block 2. What forces act on block 2?
The same.
It's actually the same set of forces. You have a tension and you have a weight, but the weight is bigger. Okay? So my downward facing arrow W for block 2, just to exaggerate it maybe, is pointing down like this. And then the tension is pointing up like this. That's not any different from before. And remember, the tension gets transmitted along the string undiminished. So it's the same amount of tension here and here. That's important to see. You got that? All right, so we have to be a bit careful. What we're trying to solve for is some acceleration, but to be clear, let's let A be the magnitude of the acceleration. And this is for both blocks. Where it's going to be understood that block 1 is accelerating upward and block 2 is accelerating down. So in other words, when it comes time to plug in an acceleration, I'm going to use positive A for block 1 and I'm going to use negative A for block 2. Okay? Make sense? Yeah.
Don't you have to add the weights on like block 1 on block 2, or is that in tension?
The tension is the force that connects them. So that actually, yeah, is this equal and opposite force that connects them. But this problem is simple enough that I'm not going to even use that notation. Okay? Okay, so we have F equals ma, and we only need to consider the y direction because there's just nothing happening in the x direction at all. And we're going to do this individually for block 1 and for block 2. So for block 1, how do we add these two forces? Well, I have a force going up, which is T, and I have another force going down, which is W1. So the net force in the y direction is the magnitude of T minus the magnitude of W1. Does that make sense? This is how we add two forces going in opposite directions, just the magnitude of T minus the magnitude of W1. And the mass, I'm going to call that M1. So I have to be careful. We have two separate masses, and I have to keep them as separate objects in my equation. Okay, what is the acceleration? Well, we're calling it A. And in this case, since we're accelerating up in the positive y direction, that gets a positive sign in my equation. Okay? So I'm going to take this one step further and just solve for the magnitude of the tension. Magnitude of T what does that equal? It equals M1 times A, this part, and then plus W1, right? I can just take weight and add it on this side. And how do I write the weight of an object? That's mg, right? So this would be m1 times g if I'm talking specifically about mass number 1, okay? We good on that? All right, so then let's look at block number 2. So let's go to our diagram. This is going to tell us how to set up our F equals ma equation. It's just like before. I have tension up, weight down, but it's not the same weight as before. This is now W2, all right? So I'll have the magnitude of my tension force minus the magnitude of W2. That's how the forces add. And that equals M2. That's the mass of that block. And then times the acceleration. But remember, this one's accelerating down. So if we're accelerating down, I have a negative sign in that. Make sense? All right, so here's what we're going to do. I'm trying to solve for A. And if you look at our equations, I have tension, which I don't know, and I have acceleration, which I don't know. Presumably, in this situation, we'd know the mass of each block. So what I'm going to do is sub this expression for t into the second equation, and then we'll be allowed to solve for A from that point, okay? So subbing in my t expression, I have m1 times A plus m1 times g. That's t. And then I'm doing minus W2. That's m2 times g, correct? That's equal to minus m2 times A. So let's just shuffle things around. Let's put all the A terms on the left side of the equation. Let's put all the G terms on the right side. So here, I have M1 times A. I'm going to add to both sides M2 times A. It puts it over here, okay? So I have M1 plus M2 times A on this side of the equation. Then what I'm going to do is I'm going to actually subtract both of these terms here to put them on this side of the equation. So I'm going to have M2 minus M1 times G, okay? That's just a reshuffling of the terms. Any questions on that? All right, so what's A? It's equal to M2 minus M1 divided by M2 plus M1, so I'm just dividing this whole thing out, times G. So that's a formula for what the acceleration will be in terms of the two masses that I have at either end of the string. And again, let's just look at this and make sure that it makes basic sense. If I had equal mass on either end, it would be balanced out, right? What would you expect the acceleration to be in that case?
Be 0.
Yeah, it'd be 0, right? Does that make sense? We have two equal masses on either end. It's not going to accelerate either way. Well, if I have two equal masses, what's M2 minus M1? It's 0, right? So it's, if they're the same mass, my acceleration is 0, as I expect, okay? Again, I'm encouraging you to look at the results you get and just try to see if they make sense. See if they agree with your intuition, okay? All right, here's A. M2 minus M1 divided by the sum of the two masses times G. That's what we have. Any questions? Yeah.
For that equation, does M2 always have to be the bigger mass?
Okay, yeah, so there's nothing special about assuming M2 is the bigger mass, right? These are just arbitrary labels we give to things, right? So, but what happens if that's not true, right? If M1 is actually the bigger mass? That means this comes out negative, right? that just means everything is accelerating in the opposite direction to what you assumed. Okay, that's what that would mean. So this is sometimes a strategy we'll take. We'll just kind of assume everything's accelerating in one direction, work out the result, and then if in the process of calculating the answer you get a negative sign, it just means, oh, must have been accelerating in the other direction. But yeah, there's nothing special about the way we're labeling things here. M1 and M2 are just arbitrary labels. All right, let's do this one and then let's get out of here. So you've probably heard of this idea of mechanical advantage before, maybe. This is an example of that. So we have a worker who has a mass of 65 kilograms who is sitting on a platform with a mass of 95 kilograms. So just to be clear, the platform is like this entire thing, including this pulley right here. So this pulley is part of the platform that moves up and down, okay? So what the worker does is he pulls down on this rope right here. And if you follow the rope, it goes through this pulley and then through that pulley, and then it's connected up here to the roof. So by pulling down on this rope, the worker is actually able to move himself upwards. And if you were to pull down on the rope and let it get slack a little bit, he'd be able to move himself down. So just by pulling up or down on the rope, the worker is able to move. Okay. So one question that we'll answer to start is, if the worker is going to move himself up, what is the total weight that needs to be lifted up? Well, that would just be the combined weight of the worker himself and the platform. So we'll calculate what that is. And then the second question is, what is the minimum force that the worker needs to apply in order to lift himself up? And here's a spoiler. This is going to be 3 times less than the total weight. So the worker actually needs to exert a lot less force than the total weight of everything that's being lifted up to actually do this. And that's because of these pulleys and the mechanical advantage they give you. So let's get into that. Let's do the first part, which is, what is the total weight that needs to be lifted up? That's pretty straightforward, right? The total weight that needs to be lifted up is the mass of the worker plus the mass of the platform times g. Right? So the combined mass times g is the combined weight that needs to be lifted. So if the worker is 65 kilograms and the platform is 95 kilograms, if we multiply that by g, which is 9.8 meters per second squared, we'll get the total weight that needs to be lifted up. So can someone punch that in and tell me what it is? $1,568. 1,568. Keep 3 sig figs, newtons, right? So let's just say 1,570 newtons. Okay. So now let's answer the second question, which is a little trickier, okay? And the second question is, what is the minimum force that the worker needs to apply in order to be lifted up? Okay, so the word minimum, let's understand what that's doing in this question, okay? So to lift something up, let's just take a more simple case where I'm just lifting something up with my hand and not a set of pulleys. Okay, if I am applying a force on, let's say, the stapler, that's equal to the weight going up, then it doesn't accelerate. We agree? Because the downward weight plus the force up that I'm applying cancels out to give you 0, right? But if I wanted to lift it up so that it accelerates like this, right? So I'm actually accelerating it up, then I would need to apply a force that's bigger than the weight to get it to accelerate up, right? But I could also just lift it up at a constant speed, like this. So if I'm lifting it up at a constant speed, how much force am I applying upwards? Is it equal to the weight of the object I'm holding or less than the weight? What do we think?
More than the weight?
So actually it's equal to the weight, because if I'm moving up at a constant speed, okay, that means we're still not accelerating. Okay, we're just moving up with a velocity that's constant and unchanging. So the minimum amount of force I need to apply to lift something up, in this case, would just be equal to the weight, right? Okay, not the case here. Let's see why. So the worker is going to pull down on this rope with some force, let's call it F. And in the process of doing that, we're going to create some tension in the rope, okay? Now let's try to see what that tension in the rope is doing to our platform and what kind of force it's exerting on our platform. So the first thing to see is that if the worker pulls down on the rope with some amount of force, the rope pulls back up on that worker with an equal and opposite amount of force, right? And that force exists all the way throughout the string. That same tension that we put in the string is present everywhere. So in other words, there's tension here, there's tension here, and there's tension here in all three of these upward facing segments of rope. Do we see that? And so because we have those three segments of rope all pulling up with the same amount of tension, we're amplifying the force by a factor of 3. Because we have three segments of rope here that are exerting that upward tension. Okay? And that's what the pulley is doing for us. So, when I draw a free body diagram of the worker plus the platform, I'm actually going to have three segments of rope pulling up, each with the same amount of tension, which I'll call T. And then I'll have the total weight going down. That make sense? And then when I do F equals ma in this situation, here's what I'm going to plug in. The net force in the y direction is going to be 3 times whatever that tension is, because I have 3 copies of that, minus W total. That's how I add the forces all together. Okay, just to do it in shorthand. Make sense? And then what do I set that equal to if I'm trying to find the minimum amount of force? I can set that to 0. Because I don't care about pulling on the rope so hard that we accelerate up. It's okay just to move up at a constant speed. So assuming we move up at a constant speed, the acceleration is going to be 0. So therefore, the tension that's needed is equal to the total weight divided by 3. So it's 1,568 newtons divided by 3. What is that equal to? Yeah. So even though the total weight that needs to be lifted up is this much, you only need to apply 1/3 of that force to actually lift up. That's the advantage of using a system of pulleys like this, okay? Any questions on that? All right, so we'll end it here.